What if the greatest discovery in human history almost happened, and then, without warning, the universe simply turned the lights off? Not a slow fade, not a technical glitch, a sudden silence. On the 15th of January 2026, something extraordinary unfolded in orbit around Earth, and for 67 hours, humanity's most advanced eyes in space went dark at the exact moment we were about to observe one of the most mysterious objects ever detected. To understand the magnitude of that moment, imagine the most powerful scientific instruments ever built by our species. Satellites worth billions of dollars, carefully positioned in the cold vacuum of space, watching distant stars and tracking objects moving through the solar system. These machines represent decades of engineering, the pinnacle of our technological capability. And yet, at exactly 1804 UTC, something happened that none of those systems were designed to explain. The spacecraft known as the Transiting Exoplanet Survey Satellite, or TESS, was preparing to lock its sensors onto an interstellar object called 3I Atlas. This visitor from deep space had already attracted enormous attention. Scientists believed that during its passage through sector 1751, TESS would capture the most detailed data ever recorded from an object entering our solar system from the interstellar void. It was the perfect observational window, a rare alignment of trajectory, position, and technology. But just as TESS prepared to begin its observation, the impossible occurred. The satellite didn't simply experience a momentary error. It didn't lose a small stream of data or produce corrupted telemetry. Instead, the entire spacecraft dropped into a deep, safe mode. Instantly, its sensors shut down and its connection to Earth went silent. The data stream disappeared for 67 hours. For scientists waiting for that information, those hours were agonizing. Yet the mystery became even deeper when researchers looked at the timeline more carefully. Because earlier that same day, something else had happened in orbit. At 14:30 UTC, several hours before the TESS blackout, the International Space Station suddenly declared an emergency. Crew operations were halted, a medical evacuation was ordered, and the mission ended months earlier than planned. Within hours, astronauts were returning to Earth. Official reports described the situation as an unspecified medical emergency requiring an immediate deorbit. But when the capsule finally splashed down and medical teams examined the crew, every astronaut was declared healthy. No illness, no injury, no explanation. Now step back and look at these two events together. The International Space Station, humanity's most important orbital laboratory, suddenly evacuates during a mysterious emergency. Hours later, the TESS satellite shuts down while observing the same interstellar object, and both incidents occurred during the exact same 6-7 hour window. According to the mathematics of statistical mechanics, the probability of these events happening purely by chance is astonishingly small. Calculations place the odds at roughly 1 in 877,000. In science, when probabilities become that extreme, we stop calling them coincidences, we begin calling them signals. And if that interpretation is correct, then the silence that surrounded January 15 wasn't simply a technical failure. It may have been the moment when something in the universe decided that humanity was looking in the wrong direction. And what happened next during those missing 67 hours might be the most important part of the story. If you're fascinated by the mysteries of deep space and want to uncover what scientists believe may have happened during that blackout, make sure you stay with me until the end of this investigation, and don't forget to like the video and subscribe for more explorations into the unknown. And if the blackout had involved only a single satellite, scientists might have written it off as an unfortunate technical malfunction, space hardware fails, sensors glitch. Electronics can behave unpredictably in the harsh environment of orbit, but what made the January 15 event so unsettling was the nature of the failure itself. In the science of orbital photometry, satellites like TESS are designed to measure incredibly small changes in light. By observing distant stars, they detect tiny dips in brightness caused by planets passing in front of them. From those faint variations in light, scientists can determine an object's rotation, its shape, and sometimes even the composition of its atmosphere. For an interstellar object like 3I Atlas, this kind of measurement would have been invaluable. TESS was positioned perfectly to capture the object's light curve as it passed through sector 1751. That data could reveal whether the object was a natural body like a comet or asteroid, or something far more unusual. But instead of collecting the most important measurements of the encounter, the satellite shut down completely. In reliability engineering, failures almost always leave a trail. When electronics malfunction, they produce warning signs, voltage spikes, temperature fluctuations, corrupted signals. Engineers expect to see symptoms that explain why a system stopped working. Yet, in this case, none of those indicators appeared. The transition was instantaneous. One moment TESS was transmitting high-fidelity data. The next moment it dropped into safe mode, cutting off its instruments as if an invisible switch had been flipped. And remarkably, the hardware itself showed no damage. Computer simulations conducted afterward suggested that only a very specific kind of disturbance could trigger that kind of shutdown without harming the satellite systems. One possibility was a localized electromagnetic pulse. Another was something far stranger, a sudden environmental change affecting the satellite's sensors at a fundamental level. Some theoretical physicists even proposed an extreme scenario involving higher dimensional disturbances, what certain string theory models describe as fluctuations connected to the 11th dimension. While these ideas remain speculative, they highlight how unusual the event truly was. But there is another interpretation that some researchers quietly discuss. Instead of a natural phenomenon causing the shutdown, the satellite may have been deliberately jammed. In modern engineering terms, this would be similar to saturating a sensor with a powerful signal so that its onboard computers cannot process the incoming data. When systems encounter contradictory or overwhelming inputs, their protective programming forces them into safe mode to prevent permanent damage. In other words, the satellite effectively shuts its own eyes. If we view the situation through what physicist Michio Kaku often describes as the Kaku scale of civilizations, the implications become unsettling. A civilization capable of harnessing the full energy of its star, or even its entire galaxy, would view our electronic technology as primitive. To them, our satellites might be no more difficult to silence than switching off a flashlight. A focused beam of coherent radiation transmitted from deep space could potentially overwhelm sensitive detectors like those aboard TESS. If such a signal existed, it would not destroy the satellite. It would simply force it to stop observing. And that raises a troubling question, because during the exact same window when TESS lost its ability to see, the International Space Station was also experiencing an emergency that forced its crew to abandon orbit. To understand why two of the most important platforms in Earth's orbital infrastructure might fail at the same time, we need to examine the environment. They share the delicate protective shield surrounding our planet known as the magnetosphere. And what scientists found there during those same hours makes the story even more difficult to dismiss. If you want to understand what the ISS instruments recorded during that evacuation and why some researchers believe the station may have become part of a much larger cosmic signal, Stay with me for the next part, and be sure to subscribe so you don't miss the rest of this investigation. The International Space Station circles Earth at an altitude of about 420 kilometers, traveling through a region protected by our planet's magnetic field. This protective bubble, known as the magnetosphere, shields astronauts from much of the dangerous radiation constantly streaming through space. Without it, long-term human presence in orbit would be impossible. Inside that shield, the ISS operates as the most advanced laboratory humanity has ever built beyond Earth. Every mission is carefully planned. Every emergency procedure is rehearsed countless times. And in the field of space medicine, one rule stands above all others. Evacuation is the last resort. Astronauts are not brought home early unless something has gone seriously wrong. This is why the sudden evacuation order issued on January 15 raised immediate questions among researchers who study orbital operations. Official reports described the situation as a medical emergency requiring an immediate return to Earth. But after the astronauts landed and underwent examination, every crew member was declared healthy. No illness was reported. No injuries were identified. No life support failures were disclosed. The details surrounding the event remained classified, and the silence from official channels only deepened the mystery. Some physicists began looking at the situation from a very different perspective. Instead of focusing on a medical explanation, they considered whether the environment around the station itself had changed. In theoretical physics, space is not empty. It is a dynamic structure woven from fields and energy. If an object moving through the solar system were capable of producing unusual vibrations in space-time, subtle resonances at extremely low frequencies, those disturbances could potentially interact with both electronics and biological systems. In other words, the station might not have been evacuated because someone was sick. It might have been evacuated because the station itself had become the problem. If 3I, Atlas, was emitting a persistent resonance, the ISS could have acted like a giant antenna. Its structure, solar panels, and electronic systems might have amplified signals originating from the object as it passed through sector 1751. That possibility becomes more intriguing when we examine the station's magnetometer data during the evacuation window. These instruments detected a sequence of pulsed ultraviolet emissions originating from the direction of the interstellar object. In spectroscopy, ultraviolet pulses are not random phenomena. They are often associated with extremely high bandwidth data transmission. In fact, UV wavelengths are sometimes used in experimental communication systems because they can carry large amounts of information. If those pulses were natural, they would likely appear chaotic and inconsistent, but the pattern recorded during those hours showed a level of structure that scientists rarely see in purely natural processes. This brings us back to the 6-7 hour blackout, because in information theory, missing data can be just as meaningful as the data itself. By losing nearly 3 days of continuous observation, humanity lost the ability to verify at least 27 documented anomalies associated with 3I, Atlas. These anomalies included unusual surface patterns resembling hexagonal tessellations and small deviations in the object's trajectory movements that did not match the predictions of classical gravitational physics. In astrodynamics, an object moving through a gravitational field follows a predictable path defined by the equations of general relativity. But if something happened during those 67 hours, something like a propulsion event or a change in trajectory, we would have no direct record of it. All we would see is the difference between where the object was before the blackout and where it appeared afterward. And that difference may hold the most disturbing clue of all. because when scientists finally regained contact with their instruments, they realized that 3I Atlas was no longer moving the way it had been before the silence began. And the physics behind that change suggests something far beyond an ordinary interstellar rock. When the data stream from TESS finally returned after 67 hours of complete silence, scientists expected to see the interstellar object continuing along the same hyperbolic trajectory it had been following before the blackout. In celestial mechanics, objects moving through the solar system obey predictable laws. Their paths bend under gravity, but the equations describing those movements are extremely precise. But the moment researchers compared the new telemetry with the previous orbital model, something didn't match. 3I Atlas had shifted. Not dramatically enough to trigger headlines immediately, but enough to force scientists to recalculate its trajectory. The object was no longer exactly where classical gravitational physics said it should be. Its path appeared to have settled into a slightly different configuration, one that suggested a maneuver had occurred during the period when our instruments were blind. In the science of ballistics, changing momentum requires energy. Rockets produce visible exhaust, comets release gas, even small asteroid impacts generate heat signatures that infrared sensors can detect. Yet when analysts reviewed the infrared data surrounding the object's position, they found no plume, no heat spike, and no measurable increase in entropy. It was as if the object had changed position without producing any conventional propulsion signature at all. Some theoretical physicists approached the puzzle through the lens of string theory. In these models, our familiar universe of 3 spatial dimensions and 1 dimension of time may be embedded within a much larger structure that includes additional dimensions beyond our direct perception. If an advanced technology could manipulate those hidden dimensions, it might not need to push against space with thrust. Instead, it could shift its position by altering the geometry of spacetime itself. Rather than moving through space, the object could move space around it. That idea might sound extreme, but it aligns with one detail that has remained consistent throughout all observations of 3I Atlas, its rotation. Sensors indicate that the object maintains a steady 7-1-hour rotational period. For a natural body tumbling through space, such stability is unusual. Most interstellar objects spin irregularly after millions of years of collisions and gravitational disturbances. But 3I Atlas rotates with the precision of a balanced system. In engineering terms, that kind of rotation could act as a form of gyroscopic stabilization. A spinning structure naturally resists changes in orientation. If the object contains internal mass or mechanical systems, that rotation could protect whatever is inside from the enormous forces produced by sudden motion. It would behave less like a drifting rock and more like a controlled platform. Some researchers have cautiously raised another possibility, one originally proposed decades ago by physicist Ronald Bracewell. In this hypothesis, advanced civilizations may deploy autonomous probes across the galaxy to observe emerging technological species. These devices, known as Bracewell probes, would not necessarily communicate immediately. Instead, they might quietly analyze a civilization's technological capabilities before deciding whether contact is appropriate. If that interpretation applies here, then the blackout on January 15 may not have been an accident at all. It may have been a test. During those 67 hours, the object could have measured our response times, our sensor limitations, and the way our institutions react under pressure. By disabling our observational systems and forcing the evacuation of the ISS, it may have learned more about our technological maturity than years of passive observation could reveal. And if that is true, then the most important question is no longer what happened during the blackout. The real question is what the object did after the silence ended. Because once tests rebooted and the ISS returned to normal operations, scientists detected something new emerging from the region where the maneuver had occurred, a signal that should not exist in nature. And that signal would lead researchers to one of the most unsettling interpretations of the entire event. At the exact moment the blackout ended, something extraordinary appeared in the data collected by the Deep Space Network. The vacuum of space, which normally produces a chaotic mixture of background noise and natural radiation, suddenly displayed a highly organized pattern. Scientists call this kind of phenomenon a coherent resonance. In signal processing, coherence means that a signal maintains a constant frequency and phase over time. Natural cosmic sources rarely behave that way. Stars fluctuate, pulsars drift slightly. Even the most stable astrophysical systems contain some level of randomness. But the resonance detected after the 6-7 hour silence was unusually clean. The signal originated from the same coordinates where 3I, Atlas, had performed its unexplained maneuver. Some researchers began considering a possibility that had previously seemed far too speculative to discuss openly. Instead of representing a malfunction or coincidence, the blackout may have been part of an intentional sequence, a controlled interaction between the object and the environment of our solar system. In the framework sometimes described by the Kaku scale, a civilization capable of harvesting the energy of an entire star would possess technologies far beyond our current understanding. Such a civilization would not merely travel through space, it would actively shape the conditions around it. From that perspective, the 6-7 hour blackout might not have been a failure of our equipment at all. It might have been a software update for our local region of space-time. While that interpretation sounds dramatic, several physical observations support the idea that something unusual happened in Earth's immediate environment during those hours. Measurements of the magnetosphere, the vast magnetic shield surrounding our planet, revealed a series of disturbances known as flux ropes. Flux ropes are twisted magnetic structures that usually appear during powerful solar storms. They form when magnetic field lines stretch and reconnect, releasing large amounts of energy. But during the blackout window, the sun was quiet. Solar observatories recorded no major flares, no coronal mass ejections, and no significant solar wind events capable of producing such disturbances. Yet Earth's magnetic field behaved as though it were being gently pulled and twisted. Some models suggest that the presence of a massive spinning object could create subtle gravitational effects that interact with magnetic fields. If 3I, Atlas was rotating rapidly while performing its maneuver, it might have generated localized frame dragging, a phenomenon predicted by general relativity in which a spinning mass slightly twists the fabric of spacetime around it. Frame dragging has been observed near black holes and neutron stars. Seeing hints of it associated with an object moving through our solar system would be unprecedented. Another anomaly involved the gravitational footprint of the object itself. After the blackout, measurements indicated that its apparent gravitational center did not perfectly align with its visible position. The discrepancy was small but consistent. If the readings are accurate, the object may be using space-time distortions to disguise its true location. In simple terms, what we see may not be exactly where it is. For centuries, astronomy has operated under a fundamental assumption. When we observe something in space, the light reaching our telescopes represents the true position of that object. But the events surrounding January 15 challenge that assumption. Because if 3I, Atlas, can manipulate space-time on a small scale, then every observation we make could be slightly offset by a distortion we cannot directly detect, and that possibility forces us to confront an uncomfortable idea. For the first time in history, humanity may not be the primary observer in our own solar system. We may be the ones being observed. And if that is the case, the final implications of the 6-7 hour silence become even more profound. As researchers continued analyzing the data collected after the blackout, a disturbing realization slowly emerged. The most important lesson from those missing 67 hours was not simply that something unusual happened in orbit. It was that our ability to observe the event had been completely controlled. In astronomy, we often assume that what our instruments record represents the objective reality of the universe. Telescopes gather light. Sensors measure radiation. Satellites track motion. The data we collect becomes the foundation of our understanding. But the January 15 blackout introduced a new possibility. What if our instruments only see what they are allowed to see? The behavior of 3I, Atlas suggests that the object may have the capability to influence the very systems we rely on to study it. By forcing TESS into safe mode and triggering the evacuation of the International Space Station, the object effectively removed every human-operated observational platform from its immediate environment. For nearly 3 days, it operated without witnesses. From the perspective of game theory, probes are often used to test the boundaries of a system. Engineers deploy them to discover weaknesses, measure response times, and analyze how a complex structure reacts to unexpected input. If 3I, Atlas, is an autonomous probe, as some researchers cautiously speculate, then the blackout could have been part of a simple diagnostic process. It measured how quickly our satellites shut down. It observed how our astronauts responded to an unexplained emergency. And it revealed how our institutions manage information when confronted with something they do not fully understand. In other words, it mapped the limits of our civilization's awareness. One detail continues to stand out in every dataset: the object's steady 7-1-hour rotation. Like a heartbeat, it remains the only constant in a sea of uncertainties. That rhythmic motion suggests a stable internal structure, possibly housing systems designed to operate for thousands or even millions of years. Whether 3I, Atlas, is a natural interstellar body or something far more advanced remains an open question. Science demands evidence, and extraordinary claims require extraordinary proof. But the events surrounding the January 15 blackout demonstrate that our current models cannot explain everything we observed. 2 independent orbital platforms failed simultaneously. A 6-7 hour gap erased the most critical observational window. An object changed trajectory without visible propulsion. And afterward, a coherent signal appeared where the maneuver occurred. Taken individually, each anomaly might be dismissed as a coincidence or instrumentation error. Taken together, they form a pattern that scientists are only beginning to examine. If 3I, Atlas, truly represents a form of technology, whether a probe, a sentinel, or something we cannot yet categorize, then humanity may be witnessing the earliest stage of a cosmic audit. Not an invasion, not a message, simply an evaluation. And until we understand who or what is conducting that evaluation, the silence of those 67 hours will remain one of the most unsettling mysteries in modern astronomy. Because somewhere in the vast symphony of the cosmos, a 3 billion-ton traveler passed through our solar system, demonstrated that it could blind our instruments whenever it chose, and then continued rotating quietly as if nothing had happened. The music of the spheres is still playing. But now we know something else may be listening. If this investigation sparked your curiosity about the deeper mysteries of the universe, make sure to like the video, subscribe to the channel, and share your thoughts in the comments, because the next discovery might arrive when we least expect it.